and the cardinality of 6a is at most 251. This is under this hypothesis. Now, can we do better? Of course, because I'm here, otherwise. So with our approach, we will improve this 40 to 61, in fact, and improve the 251 to 152. And the question is, how do we do that? And the purpose of the talk is to explain this approach and how we reach that. Again, we will revisit this example several times in the talk. So what are those Hilbert functions? So first of all, what is a standard graded algebra? Well, it's a graded algebra, and standard means the following. It's finitely generated over a field K, and in fact, it's the quotient of the polynomial algebra over K with n variables, where the grading is standard, namely the degree of the variables is 1, and J is a homogeneous ideal. So that's a standard graded algebra. The grading is standard. And so consequently, you may decompose R as a direct sum of vector space, the pieces of degree I. Of course, in degree 0, you have the field. And of course, since it's generated by the degree 1, then Ri times Rj is not only included in Ri plus j, but in fact is equal to Ri plus j. So that's the object we'll be looking at. And when you have such an object, well, of course, because of the finite generation, each Ri is a finite dimensional vector space. And of course, it's interesting to know how the dimension of these things evolve with I. So that's the Hilbert function. So the Hilbert function of a standard graded algebra is just the map, which gives you for each I the dimension of the homogeneous piece of degree I in the algebra. That's the Hilbert function of R. Oh, by the way, yeah, let me make a parenthesis. This is the Hilbert function. The Hilbert polynomial is, in fact, well, you can prove that this thing here becomes a polynomial for I large. And this is the Hilbert polynomial, is this function which stabilizes to a polynomial when I is large. But otherwise, the Hilbert function is this function, which is here. Okay, and so the question is, how can you characterize a numerical function which encodes this dimension for any standard graded algebra? And the wonderful thing is that Macaulay proved a wonderful theorem which gives a complete characterization, in fact, of this function. And I will explain this characterization in the talk. So for instance, at least we can say the following. Assume the dimension of R1 is n. Then in degree 2, since it's generated by products of a basis of degree 1, then the dimension in degree 2 cannot exceed the binomial n plus 1 over 2 because it's commutative. Think about the polynomial algebra. For the polynomial algebra, you would have an equality here, And so let me encode this as follows. It means if D1 is equal to this binomial coefficient, then D2 is bounded above by n plus 1 over 2. And now the great thing is that 2, I write it as 1 plus 1. This is very important for the sequel. You will see why in a minute. So remember that implication. if D1 is encoded by the binomial coefficient N1, then D2 is bounded above by the same coefficient where I add 1 to the top and the bottom. Okay, so in fact, Macaulay's theorem is a generalization of this easy fact, a wonderful generation of this easy fact. So I need to introduce a binomial representation. Take a positive integer, and take I another positive integer. Then there's a unique expression of A as a sum of I binomials, A, K, K, where K just goes from I to I minus 1 to 1. And on the top, those integers are decreasing non-negative integers from AI to 0. So there is a unique expression. I will give an example later on.
Does this mean for every I, there's a unique expression?
Yes, you fix A, and then for every I, you have a unique expression like that. I will give an example, and the example will show how to produce this expression, and the unicity is not difficult. We then define, so that's Macaulay's idea. Then when you have this unique expression, you define that symbol. So you have, again, a sum of I binomials, the same as before, but in each summand, you add +1 on top and +1 on the bottom. Oh, by the way, these slides, I will make them available in one way or another, just to let you know. So that's the operation which goes from A with I given to AI. And here's an example. I claim you take 100 with 5 here, and you get 152. Let me explain that example in the next slide. And you will understand how to produce then this binomial expression. So you fix A equals 100, and you take I equals 5. So then the fifth binomial representation of 100, this unique representation of 100, you do the following. You take 100 and you look at so 5 is fixed, and you take the largest possible one here so that this binomial does not exceed 100. So in fact, 8, 5 is 56, that's okay. It's less than 100. And if you had taken 9, then this is 126, 126, and so 9 does not qualify. So you take the largest. Now you take the difference, 100 minus 56, which is 34, and now you fix 4, and the largest which qualifies is 7. Now you take 3, you take 100 minus these 2, I don't remember how much it is, but you take 3 then, and the largest which qualifies is 4. And then the largest which qualifies for 2 is 3, the largest which qualifies for 2 is 1, and that's your representation, okay? And now we apply Macaulay's construction, 100, qu'est-ce qui se passe ici? 105, you add 1 everywhere on top and on bottom. So by definition, this is 96 plus 84 and so on. And when you do the sum, you find 152. So that's the example, and that's the procedure to produce this unique representation. Okay, and from this little computation with our method, we shall deduce the following. If you have any set A in an abelian group so that the cardinality of 5A is 100, then the cardinality of 6A, whatever happens, can never exceed 152. So that's what we want to explain here. So to do that, we shall need Macaulay's theorem. Here is the first half. So as I said, it characterizes the Hilbert functions of standard graded algebras. And here's the necessary condition. So take any standard graded algebra over a field K with with Hilbert function di. No, sorry. Then for all I, the piece of degree I plus 1 is bounded above by the piece of degree I submitted to that operation. So that's the necessary condition in Macaulay's theorem. And example again, so take any standard graded algebra, assume the dimension of the piece of degree 5 is 100, then Macaulay states that, and d5 is 100, we've seen that in the preceding slide, and therefore the piece of degree 6 can never exceed 152. Okay, so let me state the full theorem. Simply, the full version is that that necessary condition is in fact sufficient. So take any numerical function from n to n, associating to I a natural number di, and that numerical function is the Hilbert function of some standard graded algebra. So if and only if in degree 0, in d0 is 1, of course, and these necessary condition hold. This is a remarkable theorem. Let me give an example. Let me just give 7 numbers: 1, 5, 15, 33, 61, 100 again. This is the piece of degree 5, and 162 as the 6th number in the sequence. Then you can check that these conditions are met, are satisfied for all I from 1 to 5. Hence, by the sufficiency of this condition in Macaulay's full theorem, there must exist some standard graded algebra such that at least for these 7 values, this holds. And let me give you a concrete example. You take the polynomial algebra in 5 variables and you mod out, you kill these 3 monomials, x5 cube, x4, x5 square in degree 3, and in degree 5, x3 cube, x5 square. And I guarantee you that the piece of degree 0, piece of degree 1, up to piece of degree 6 is exactly given by these 6 numbers.
Is this a homogeneous ideal?
Yes. Yes, because it's generated by homogeneous polynomials.
Oh, so
they do not have the same degree.
Yeah.
Yeah, exactly. It is a homogeneous ideal because it's generated by homogeneous polynomials of various degrees. So yeah, so let me go back. So in fact, in this talk, we use Macaulay's theorem as a black box, but especially for you, Mel, because of an earlier mail, let me give you a glimpse into the black box.
Thank you.
So you're welcome. So denote MD the set of monomials of degree D in n variables. And now you order MD lexicographically. So X1D is the largest one. The next one, of course, is X1D minus 1 X2. I need to give you the largest one after that because in order not to confuse with the reverse Lex order. So the next one is X1D minus 1 X3, and so on and so forth. And the smallest one is X1 to the D. So that's the Lex order on MD. Now, what is a Lex segment in MD? Is just a sequence of all the largest, all the monomials which are larger or equal than some given monomial of degree D. So for example, a Lex segment of length 1, there is only one, it's this one. A Lex segment of length 2 is just the first two one. A Lex segment of length 3, there is no choice, it's just these first three monomials, and so on. So a Lex segment of length k, there is only one, and you take, starting from the largest one, you take the k largest ones, and this is a Lex segment, okay? Okay, now denote M. M is M1, all the variables of, all the monomials of degree 1. And now, of course, if you have a bunch of monomials of degree D, then you multiply them by the variables and you get a bunch of monomials of degree 1 more, okay? And now, if A was a Lex segment, L, then you do this operation and it is easy to see that this gives you a Lex segment of degree 1 more, but it's a Lex segment again. And now, now the key point, this is the key point in Macaulay's theorem. Lex segments have minimal growth. What does it mean? It means that if you take A and L, two subsets of monomials, A arbitrary, but L a Lex segment, and assume they have the same cardinality. So in fact, you start with A, you compute the cardinality, and you take the Lex segment with that cardinality. Then these two you multiply by the variables, and then you have this inequality here. So that's the key point. Lex segments have minimal growth. So you can think of the integers, for example, and well, if you multiply a finite, if you take the sum set of a finite set with an interval, the growth is smallest possible. So that's the same thing in multiplicative. This is multiplicative combinatorics. And now let me introduce a notation. Take any bunch of monomials, and I denote A bar the complement. Okay. Now take a Lex segment, L, and take the complement. And count how many there are in the complement of the Lex segment, and call that cardinality A. Now you multiply the Lex segment by the variables. This is the Lex segment in degree D plus 1. And take the complement. And the question is, what is the cardinality of that? knowing that it was A here. So what is the cardinality of that? And the answer is, this is suspense. The answer is, that's the answer. This is where it comes from. This is how Macaulay invented that operation, exactly by doing these counts. And in fact, if you gather all these 8 observations or whatever, then in fact, these are the ingredients in Macaulay's theorem. The key point is the number 6, of course. Leg segments have minimal growth. And this is where the proof is hardest, but that's the theorem. Okay, so that was, now we close back the black box and we can just exploit Macaulay's theorem as a black box. And let me do what we promised to do, construct an algebra whose Hilbert function will model the sequence of cardinalities of the iterated sum sets of A. So take an abelian group, G, a commutative field K, take a finite non-empty subset in your abelian group, and the algebra we want to associate is defined as follows. We will define such an algebra in such a way that its Hilbert function will model what we want to model. So let me explain how this algebra is constructed. First of all, you take the group algebra of G over K. What is that? Well, it has a canonical basis. It has one symbol for every element of the group. And what's the product in this algebra? Well, it's a vector space, so you know the sum, but what's the product? It's simply induced by the product of these two symbols. T to the power G1 times T to the power G2 is just T to the power G1 plus G2 in your group. That's it. So this completely describes the group algebra. It's a vector space over K. And the product is defined this way. Okay, now you take over this group algebra, you take the polynomial algebra over Kg. Call that S. And in the next slide, I will describe again basis as a vector space of S. That's easy enough because you have, you know, a basis here, you know, a basis, the power of X over K. You just combine these two bases. So I go to the next slide. A natural K basis for S is simply the set of all symbols T to the power G, X to the power N, where G belongs to the group and N is a non-negative integer. So that's the K basis. And what is a product? Easy enough. The product of two symbols is what you think. And so that's a natural K basis for S. And now I want to define the degree of such a basis element. Well, you see, let me go back to the previous slide. So this is S, is the polynomial algebra over Kg. So Kg is the coefficients and X is a variable. So the coefficients should have degree 0. And this is what we do. Coefficients will have degree 0. So you see Tg, consider T to have degree 0, so Tg has degree 0. The degree of Tg xn is just n. Okay. And this induces a grading on S, and simply what is the part of degree h is just the set, it's just the set of all tg times xh when G belongs to the group. You see, I didn't say it's a standard graded algebra because if the group is finite, then this is not a finite set. But it's a graded algebra. SH times SH prime is contained in SH plus SH plus H prime. Okay, so that's it. Okay, now take your subset A of the group. I call A1, AN the elements of A. And now this is what we wanted. You define array to be the K subalgebra of S spanned by this finite set. So this is all degree 1, homogeneous of degree 1. And that means that, in fact, array is a subalgebra of S spanned by TA1x, TANX. So that's the algebra array. And now I claim that this is a standard graded algebra, and its Hilbert function exactly models what we wanted to model. So indeed, if you fix h, a non-negative integer, Rh is a vector space with basis t to the power b xh, where b runs over the iterated subset HA. Let me give an example with h equals 2. So you see R2, this is a piece of degree 2 in R. The basis is just that. Why? Because look, these are your generators of degree 1 in R. If you want degree 2, you have to multiply together just 2 guys among those. So it's TAI x times TAJ x, which is T times T to the power AI plus AJ x squared, you see. So here it is clear that the dimension of R2 is exactly the cardinality of the set, which is A plus A. And this works for any H. And hence, this is exactly what we wanted. So this is wonderful. So now we have a standard graded algebra, and its Hilbert function models what we wanted to model. And now the miracle is that we have an old theorem, 93 years old theorem, which gives necessary and sufficient condition for a numerical function to be a Hilbert function. So we shall just apply them to that. So let's go to the next slide. Let's first revisit the example. That was a famous example, a set of integers whose cardinality of the fifth iterated subset is 100. So take the associated graded algebra to that set A. So it means in degree 5 we have dimension 100. Now Macaulay says, well, the dimension of the piece of degree 6 is no more than this operation, which we computed explicitly. It was 152. But this dimension is just 6a. Well, here I cannot see. Yeah, so it means that 6a is at most 152. What about 4a? Well, I claim the dimension is at least 61. How do we know? Because assume it was at most 60. Then take the fourth binomial representation of 60, and I claim here it is. Now you do the count, and the count gives you 98. But 98 is not enough to reach 100. Macaulay tells us, well, then if that was true, then the part of degree 5, its dimension would not exceed 998. This is Macaulay's theorem, which contradicts the 100. So therefore, it is impossible that the piece of degree 4 should have dimension at most 60. So thus proves the claim. So here's the summary of what we found, and something which I said earlier already, but here's the summary. Assume you have a set so that this holds, then a lower bound for 4a and an upper bound for 6a. I repeat, Plünnecke gives 40 and 251 respectively. And now with Macaulay, and our approach with Macaulay improves 40 to 61 and improves 251 to 152. So that's what we got. Okay, so what comes next? Oh, a little question about optimality. This bound we just found on the previous slide, 61 and 152, provided 5a is 100. So are they best possible, at least over z? And in fact, we don't know yet. Probably they are not optimal, but at least c, they are not far to being optimal, because here is a concrete example. Take the set 0, 1, 4, 9, and 45. So let's do the count. If you take the fifth iterated subset, you will find, I guarantee it, you will find 100 elements. So this is what was wanted. And 4a, you find, in fact, 63 elements. So this is not bad. This is not very far from 61. And for 6a, we find 143, which is not too far from the upper bound. And so here's a question. Is there a subset of integers, at least, such that 5a has cardinality 100, but 4a and 6a reach the best possible ones given by Macaulay? We don't know. I think the answer is no, but we don't know. If we change the group, or then maybe we can do better, but let me leave the question like this way. Okay, so let me go to the next slide. Yeah, so I promised that we would recover Plünnecke's estimate and later on improve it. So take A in Z, it could be in fact any abelian group here. In fact, take any finite subset of an abelian group of cardinality of at least 2, let H be at least 2. Then recall this was the estimate by Plünnecke, a lower bound for H minus 1A in terms of HA. And here is how we recover this estimate, and we shall improve it. This is the same terms, but there is a factor here, a new factor here, theta of xh. So what is x? In fact, this I will define it later. This is some well-defined real number, which is at least 1, and it is defined. It depends on the cardinality of HA and on H. I will explain later what this X is. So this is our improvement, and in 1 or 2 slides, we will show that in fact this is strictly more than 1. So this is in fact a strict improvement. But in order to get that, we don't know how to get it from Macaulay's theorem proper, but we can get it from a recent condensed version of it, which involves these generalized binomial coefficients. So let me recall what that is. Binomial coefficients where the top is no longer an integer, but a variable, say. You know that very well. Xh, you can even take a variable, is just defined as if x was an integer. And okay, so you know that. But here's a lemma: fix an integer h, positive integer h, then the map associating to a real number y, thus binomial yh, is an increasing bijection from the real interval h minus 1 to infinity in bijection with the non-negative real numbers. And in particular, it has this monotonicity property here. And this is a direct consequence of Roth theorem because the roots are simple here, so that's easy enough. And here's a corollary. We shall need very much this corollary. If you take a positive integer and any real number z here, then you take the inverse bijection. It means there exists a unique real number h in this interval such that z is obtained from this bijection. So we will need that a lot, because for suitable z, we will need to represent z given h. We will need to represent z in this way. Okay. So, in fact, if this is, say, a positive integer or any real number at least 1, then in fact this unique h is at least h. We will need that too. Okay, so here is a condensed version of Macaulay. In fact, it was invented, it was discovered 3 years ago, 3 years ago, to apply Macaulay to a beautiful conjecture in numerical semigroup theory, a conjecture by Wilf. And the conjecture is still a conjecture, but this version of Macaulay allowed me to give an asymptotic proof of the conjecture. And so take a standard graded algebra. I cannot read here. Let x be the unique real number such that you represent the dimension of Ri in this way. So this is where we need the corollary of the previous slide. This is where x comes from. It's unique, and given I, it allows to represent this dimension in this way. So then a lower bound for the piece of degree 1 less is this, and an upper bound for the degree of piece 1 more is this. So you see again, you see again this +1, but it's simpler than in Macaulay because you don't have this sum of binomials. You just have one binomial, and so this is simpler. It's, of course, there's a little loss of information here, definitely, but it's a little loss of information, but on the other hand, it's more flexible to get consequences. So here in particular, we will need that condensed version to derive Plünnecke's estimate. And now that's the key number. You remember the strengthening factor, theta of xh, it's defined in this way. H over x times this binomial to the power 1 over h. So that's theta of xh. And now we can prove the theorem in the next slide. And the theorem was, so this was what was announced with this factor, but now we know what is x. Now x is the unique real number, at least h, such that you can represent HA as a binomial xh. And so now we know what is x, and we know what is theta. It was defined in the previous slide. And moreover, this thing is at least one. So let me go over the proof. Condensed Macaulay directly gives us lower bounds because we have this graded algebra array. And now, as usual, you can represent this binomial coefficient in this way because you see xh is defined this way. Now you isolate the term with I equals 0. This is x over h times the remaining terms, and this is this one. So you know these formulas. This is simple enough. Let me use it in the next slide. And so hence, so this was without the power h, this was given by condensed Macaulay. We erase everything to the power h, it gives this. And now here, recall the definition. Yeah, recall the formula of last slide, this is that. Now here we isolate one factor. And now remember, this is theta, in fact, to the power h. This is theta to the power h. And this one, again, is what we started with. And now you take h roots and you get exactly what we wanted to get. Okay. And it remains to show that, you see, if this factor was 0, we would not get very far, but in fact, let's show it's at least 1. This is in the next slide. In order to show it's 1, let's raise it to the power h and show that this power h is at least 1. So the power h was that by definition, and this was that by definition, and now it's simple enough. The numerator is at least as much as the denominator because of that, and here it is. So this gives the proof, and so we recovered Plünnecke. But in fact, I claim we strengthen it a little bit. In fact, if x is strictly more than h, then theta is strictly more than 1. But on the other hand, it can never exceed e, the basis of natural logarithm. Let me show that. No, let me not show that. It's a simple, just elementary manipulation. Sorry, I accelerate a little bit because there is another talk at 6, right? Maybe. So this is elementary manipulation, and okay, and here the same proof gives that it's at least 1 because there is at least one fraction where the numerator is strictly more than the denominator. Okay, so let me, it's so nearly finished, just a little bit about the asymptotic behavior of this factor theta xh. I claim this is e times the strange thing. And in particular, if you let x go to infinity, then you get this multiple of e, 2ph inverse to the power 1 over h inverse. And simply this uses the approximation of the factorial by Stirling, and this approximation of the binomial coefficient, which you can find in Wikipedia. Okay, so that's the behavior, and then also, this factor, in fact, quite often is above 2. In fact, and you can derive this from Stirling. And here is a beautiful, here's a graphical depiction of the function theta for x equals 1000. You see, when h is small, it grows very, 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 very fast. But of course, it cannot exceed 2.771. And then it decreases slowly, rather slowly. So this is very good because it means that this improvement factor, in fact, gets very strong already for small h. You see, when we pass from 40 to 61, it was improvement 1.5. 1.5 is here, and it means you reach this improvement already with h very small. In our case, it was h equals 4 or 5. And you see, this is interesting because it means this factor theta, in fact, is above 2 about half of the time, which we see here in the picture, because this is 1000 over 2, 500, and for 500 we're above 2. So we are above 2 for a long time. And it means this improvement factor theta, in fact, is for a long time is twice better than Plünnecke. Here is numerical behavior. You see, you get an improvement of at least 1.5 already for h equals 3, which we could guess from this picture. This picture was for x equals 1000, but in fact, the shape is the same almost for all x. So this is a generic shape when x is large. And so therefore, this is good. Well, you see this improvement. If you want to reach at least 2.7, then this happens here, and at least 2.71, this happens here. Anyway, this is all in the preprint, which is available on Archive. And I will make the slides available. We'll see with Eliahou. And here is a theoretical and numerical evidence that, in fact, when you take the square root of x, this is where you reach E. Okay, and that's it. In fact, the next slide is just some references. Since I have 4 minutes, let me comment a little bit. In this paper, 2018, this is where I got this condensed version of Macaulay's theorem, which was so handy. This is a preprint with Ishita on Archive. In this book by Herzog and Hibby, monomial ideals, you can have more information on Macaulay's theorem and many more things, but there is a paragraph on Macaulay's theorem. This is Macaulay's original paper in 1927. I don't know if you know this book. I leave it to you to discover it by some mathematician. I don't know what MB stands for, but Nathanson, I know it. And this is Plünnecke's paper in 1970. And this is another book on additive combinatorics by Tao and Wu. Thank you for your attention.
Oh. Thank you. So if there are any questions, you need to just unmute yourself. I don't think I know how to do that. And so I do have one question,
Yes.
which is, so what was Macaulay doing that led to this result? I assume it was certainly not in the language of graded algebras, but I don't know.
Oh yeah, he was. Oh, yes, yes. Oh, yes, he was. Well, I mean, it was for algebraic geometry purposes. But yes, it was really about graded algebra and understand how the Hilbert function grows. Absolutely.
Oh, okay. So if there are no questions,
There is a question in the chat.
Ooh, how complicated is this? Question. Do you know what happens in case of non-abelian groups?
No. No. I mean, if you take a solvable group, things are simpler, a little bit simpler. But anyway, it's much more complicated when it's not non-abelian. So the answer, I prefer to say no, plain no.
Mm-hmm. Does anyone know any non-commutative version of Hilbert functions and Hilbert polynomials? Okay, so ooh, there's another question in the chat. Oh, it's the same question. So bye, Steve. So again, thank you, Shalom. I think I recorded your talk about 5 or 10 minutes into it when I realized there was a button to push to record.
Okay.
And there is also a website for the number theory seminar, and which Dick Bumby manages. And if you want to send me the slides, I can pass them on to him and see if he can post them there.
Yes, sure. There is a possibility I can either send exactly those slides with the pause, but then it would be hard to print if one wants to print. It's easier to follow on screen, or I can send the version without the pause. It's as you wish.
Yeah, I would
or I
take out
can
the
send
pause
both.
because it's always much easier to follow slides on your own computer without the pauses there.
Perfect. So I send you with pause, right?
No, without.
Oh, without. Okay.
Yes, without. And if anyone is interested in giving a talk in this very informal summer seminar, just send me an email and let me know. If there are no other questions or comments, let me thank everyone again for joining us. Stay well and hope to see and be seen soon.
Thank you. Stay well too, everybody. Bye-bye.
Bye.
Bye.
And thank you, Mel, for organizing this.
Less work than doing a CAN conference.
Bye.
If anyone can still hear me, if you go to additive combinatorics seminar, you will hear about the great result on arithmetic progressions of primes extended to divergent series. Yes.
Bye-bye.
Bye.
Bye-bye. Hey, Eric, what's going on? Core, is that Eric?
No, this is Valdemar.
Oh, yes. Okay.
He's getting a little wait and see. Yeah, no. The TV's taking care of Eric right now.
How's my girl Freya?
Hmm?
How is Freya?
She's very good. I say that they're all home with me. Whatever their mother is doing, they claim is essential work.
Of course it is.
So they have to deal with daddy. But it's all right. It's not the best outdoor weather today, but other than that, we just get to play a lot outside, which is nice.
There was an article, a letter in the New York Times that said teaching in college was essential work, and we should all be forced to go in and meet classes with our students. They didn't discuss the danger to the students, but it said we were essential workers.
Okay, I mean, I'm happy to. Right now, I'm unemployed, so so I'm happy to have any essential work.
You're not adjuncting at Lehman in the fall.
Well, I planned this not very well because when I thought that I was graduating, I told Lehman that I would also stop being an adjunct. But then this Corona hit and nobody's hiring anything, so maybe I should have just stuck around as an adjunct. I'm going to send Farah an email and ask if he has any.
I mean, there's supposed to be some kind of freeze or at least partial freeze on hiring adjuncts. But, you know, they always can try and make exceptions.
Yeah, well, I mean, I shot myself in the foot a little bit. Well, I didn't know that we were going to be on a worldwide lockdown, but I would have been able to keep the adjunct position for sure. He asked me, but then I said, so I quit prematurely. But yeah, we'll see. They might want someone to teach a course.
In the last list that I look at, they had some unassigned classes. I don't know what that
they
means.
did?
There were a few.
Okay, I'll send Joe an email. I should try to figure that out.
By
All
the
right,
way,
everybody, I gotta go, which means I gotta shut this down.
All right. Well,
all right.
Everybody take care.
look forward to see you again.
Bye-bye.